Thanks, everybody. Thank you so much for your interest in learning more about these changes to the HRRR and the RAP. So I've got at least two of my colleagues, Curtis Alexander, who's the lead of the HRRR RAP development project, the division chief now in Global Systems Lab, and Ed Zoke, who's helped a lot with these case studies, is online here, but just quite a crew of dozens here that are involved in that, both at GSL, but also at NSEP in particular, NCO, NCAR as part of that. So let me see if I can get the advances. Yeah, so here's our quick outline. I'm going to give an overview about these changes, talk especially about the physics changes, which have a lot to do with clouds in the boundary layer. That has implications for both summer and winter. Look at some cases all from summer 2019. Talk a little bit more about the smoke and that being involved. Even though you guys are central region, you still have smoke sometimes too. Talk a little bit about the experimental HRRR ensemble, which is not going to operations, but it's good to just give you a quick update on that, and then show you the statistics on that should be, in fact, that is what it should be, HRRRv4, the new one, versus the HRRRv3, and near ceiling and near surface and ceiling forecast. So I'll stop at a couple places along the way. How long do you want me to take here, Justin? Should we target for ending by 10:45, or tell me what you'd like?
Well, so we're kind of allocated out to noon Central Time. So
okay, so we can take our time a little bit, and so I'll stop at a couple points and let people interrupt, and we can try to make it more conversational. Sound okay?
Yeah, I think that's okay.
Great. Okay. So first of all, a crew of people. This picture is a little bit older now, but Curtis is right there in the middle. But lots of people have been working both in the data simulation and the modeling also. George Grell is in the middle. Can you see my cursor, by the way? Can you see that?
Yes, we can see it.
Yeah, so there's Curtis there, there's George there. So, but a great team of people, but again, working with folks from NSEP also in this whole team. So here's our overview. We've got the rapid refresh. It's running all over all of North America, updating every hour. We have the CONUS HRRR model that's running at 3 kilometers, but also starting with the last implementation, the HRRR Alaska running also. And so these kind of busy slide here shows some other experimental things that we've been doing with the HRRR model. The one thing I'll point out in particular is this application of the 3D ensemble data simulation that takes place, and it actually drives then this experimental HRRR ensemble. But for this talk here, we're going to be talking just about this part of it, the update to the RAPv5 and the HRRRv4, which is now scheduled for the 26th of May, so 3 weeks from yesterday. So here's our applications overall, looking at the history with this implementation. So here we are right now. In fact, it looks like, see if I can get that out of the way here, with the implementation now in Q3 of 2020 of the RAPv5, HRRRv4. But these different applications have grown from aviation through severe weather, energy, hydrology, feeding the national water model, and also be a key area for WPC, flash flood forecasting, air quality now with the smoke being involved, and now coupling as well, increased coupling because of the lake interaction that I'll tell you more about. So just a quick, anticipate a couple of questions here, shortcomings from the HRRRv3. It's been running out to 36 hours. Actually, that was an improvement back in July 2018, an extension from the previous 18 hours. So that was actually a doubling of the run time, run duration every 6 hours. In HRRRv4, though, it's going to be going out to 48 hours every 6 hours. So that really gives a full day 2 coverage in what's going to be running in the operational HRRR. There have been issues all along. I mean, the HRRR's made a lot of progress over the last several years, and convective storm prediction, but there have been continued issues. And maybe one thing that we had heard a lot about and seen ourselves is this kind of maybe a poor forecast in the 2 to 6 hour range. And we think that that has really been addressed very well with this 3 kilometer ensemble data assimilation, having a more coherent structure of ongoing convection coming out of that ensemble data assimilation. There's been an issue about daytime warm bias and excessive low cloud erosion in the diurnal cycle. This is really kind of a breakthrough area, having a much better representation of subgrid scale clouds. So I'll definitely spend some time in that. Have we had any guidance in smoke in the past? No, but now that's being added, and it interacts with the overall boundary layer budget. Also, it affects radiation. So that is a key area as well. So here are the observations that we have going into the HRRR. Just to give a quick background on this, obviously we have the profiles coming in, even from some boundary layer profilers, certainly the BAD wins. The radar data itself, the radial velocity, the 3D reflectivity, and lightning is actually used as kind of a proxy reflectivity also, along with the data assimilation. The aircraft have been a very key aspect to improving the overall 3D structure of winds, temperature, and even to some extent the water vapor. The surface obs have been important, and part of the, I guess, the effectiveness in using this in the data assimilation has been producing kind of pseudo observations through the boundary layer and using that to more effectively get the impact from the surface observations. There's been an increase in the use of satellite data over the last several years, especially in bringing in more and more radiance information. The cloud top pressure and temperature is pretty critical data set as well. The AMVs go into the HRRR and the RAP as well. So this is kind of a summary overall of these changes that are going in. In the model, I'll be talking about this a little bit more. It's using a new version of the WRF-ARW. It's good to point out this is the last use of the WRF-ARW. It served us well. We're looking ahead to 2023, where we will move to an FV3 UFS version of the rapid refresh forecast system. But it's been pretty critical, as you know, for the last 10 years to be able to use WRF-ARW in the RAP and the HRRR. So there are physics changes, improvements in the boundary layer. I'll talk about that some. The use of the smoke information, improved land surface and snow modeling, which has been important for near temperature fields, especially in winter. An improved version of the Grell-Hiatus convective scheme used for the RAP. Inclusion of lake, a model for small lakes, also coupling with the Great Lakes model from the National Ocean Survey or Service, along with the Great Lakes Lab. Changes in the drag coefficient, some changes in the numerics overall, which I'll say more about. In the data assimilation, bringing in new radiance information overall, really using, in essence, kind of a data assimilation using this fire radiated power, the hot spots from VIIRS and MODIS showing up. And really the biggest change is this one right here with the 3 kilometer ensemble data assimilation. So we'll describe that a little bit with these 36 members that are running out to 1 hour, that are really driving the improved representation of the forecast error covariance. The extensions taking place also, the RAP going up to 51 in support of the 48-hour HRRR, again, every 6 hours. In the land surface itself, switching to an improved MODIS albedo data set, use of fractional sea and lake ice concentration, which we had not been using in the past. More important, I guess, for Alaska. This is really a critical area for a central region here with the use of the Great Lakes model to improve the representation of the temperature and ice concentration in the Great Lakes. I think I'll move on from there. So this is kind of a way of looking at all of the components, resolution, but certainly in the physics, in the data assimilation. And I'm now going to advance this to highlight these key areas using advanced versions of the WRF model, using for the HRRR data assimilation, this HRRR DAS the 3 kilometer ensemble data assimilation. The Cumulus is an improved version in the RAP with the Grell-Freitas scheme. This is a big area here with the work in the MYNN PBL, and some improvements also to the land surface model, which is a 9-layer model and 2-layer snow model running within the HRRR and the RAP. Some changes is actually in the diffusion as well. Also, the diffusion flipping back and forth for the HRRR model has now been decreased for momentum, and especially for just a little bit remaining here for hydrometeors, but that was quite strong before, so that makes a difference for also bands of snow bands, LES, lake effect, or other kind of winter storm, and also a change in this use of a microphysics tendency limit and eliminating that completely. So this is the way we've been initializing the HRRR from the RAP here right now, and kind of using information from the RAP going in and feeding off into the HRRR model. This is the current setup, and then having a 1-hour spin up using reflectivity data every 15 minutes, then doing another application of the data assimilation, and out of that getting the final state that's used for the 18 or 36-hour forecast. But that's now being changed. So let me flip this. Now we break this tie here. So the links between the RAP and the HRRR are really decreased now. They are there still, but the HRRR DAS here then is actually running on its own. It's cycling on its own, and then having these 1-hour pre-forecast, a mean from these 36 members is used, again with the same injection of latent heating from reflectivity every 15 minutes. So this part here is sort of the same, but this is the big difference right here now in using the HRRR DAS to start that 1-hour spin-up cycle. The HRRR data assimilation system, again, we're running here basically this 15 and 3 kilometer 36 member ensemble here, out of which then we get these little variations in how temperature, water vapor, wind fields, errors are correlated with each other at a particular time, and that's how we're able to use a more effective data assimilation to be able to do that. There are separate presentations that we can go into, and we can't really go into that too much here right now, but this actually has been developed by David Dowell, Curtis, other people in our group here over the last few years, and it's expensive. It about doubles the cost of the HRRR model allocation at NSEP overall, but it's definitely worth it with this improvement, especially for summer storms, but also for winter storms and having this improved data assimilation running now at 3 kilometers. Here's one example just to quickly show that kind of a tough situation. I think all of my cases are from last summer, but they're interesting ones. This is a kind of a tough double bow echo situation here in the Midwest over Iowa into Missouri. And so we have actually on the right side here is from the operational HRRR, which had some idea of maybe on some of the forecast a double structure, but completely missing it on many of them. So this is the 12-hour forecast from the operational HRRR, in this case last summer. But in the 12-hour forecast, actually from the HRRRv4 with the HRRR DAS, starting to be able to get some clue. It's not separated properly, but having this double structure in this derecho bow echo system was more or less captured in the 12, 9, 6, and 3-hour forecasts for this situation. So having this HRRR DAS, this 3 kilometer, of course, we're using it to drive the deterministic HRRR model. That's part of what you will see in the operational improvement. But also, as we already said, it's going to be experimentally driving the HRRR ensemble prediction run experimentally at GSL, certainly through the late summer period through the flash flood season. It also is driving the experimental Warn-On forecast, providing initial conditions and boundary conditions for that. And then also it allows us to be able to do a better job in this experimental 3D version of RTMA. Tell you what, I'll stop right there. Any questions in any of that so far?
So I don't see any yet
Okay.
at this time.
Okay, great. Thanks, Justin. We're going to talk a little bit more about the model now and what are the changes are. Our colleagues at NSSL have been working with the WRF model to have a different way of doing the vertical advection in the model with what's called an implicit explicit solution for that. And that allows us to be able to have stronger vertical velocities in the convective scheme, and also out of that having higher values of updraft helicity and actually improved supercell longevity overall. So this is really the key area to look at. This is the max updraft helicity over the previous hour from this case this actually is from a couple of summers ago, in fact, 1 May 2018. So this is actually looking with the HRRR version, but with the IEVA, vertical advection, and being able to have these really strong updraft helicity and over longer periods over what was possible with the HRRRv3. And so our colleagues at NSSL and in our own group did these experiments to be able to see that, and that's definitely shown up overall in the behavior of HRRRv4. So it's a really an important addition out of the numerics. One other area in physics that we spent some time on, we've had problems over the years, actually, people complaining about temperatures, 2-meter temperatures near lakes, sometimes dew points as well. And so this is actually a little annotation of the places where we remember hearing complaints over the last maybe 15 years, even back into the Ruck era. I circled here Lake McConaughey, which is actually shown up with the Denver office, but definitely many issues in the upper Midwest with different lake problems out of that. So out of that, we've then moved to 2 interactions. One is with the Great Lakes to improve the Great Lakes temperatures, but then also running a small lake model within the WRF model called the CLM model, and allowing the temperatures in the small lakes to evolve over time. And that actually has been quite effective, we think. So see if I can get this to move on here. There we go. This is actually an example from last summer here, looking at differences in the Great Lake temperatures. So there's sort of 2 parts here again. One is from this interaction with the Great Lakes lab, and that's going into NCEP also. It already is running at NCEP in part, but having this coupling to take place from the Lake FV model. And then the second part is to have this cycling here within the model, kind of like a land surface model, but for lakes, with the community land model, small lake model. So that is running here. You can see in this case from the HRRR at NCEP having these water temperatures over Minnesota, in Wisconsin also, with temperatures that are down into maybe 50s, and even actually these are down into the 40s here. These are inappropriate temperatures for July the 16th, as in this case. This is an example here comparing, zooming in from Lake Winnebago here. So the HRRRv was using values here, basically just extracting that using the previous technique from the Great Lakes itself, but the Great Lakes are a lot deeper, so they don't move as quickly seasonally. And so that was down in the 60s, but running the HRRX with this interactive lake model had it up to in the low 80s, which I think was the appropriate one in this case. You can also see in this case here a difference in the Lake Michigan model. This is actually from using coupling with the FV model. So the FV models knows that there are offshore winds here causing this upwelling with much colder temperatures in this case. And that turned out to be an excellent forecast. This is looking at the lake temperature from a NOAA buoy that's just east of Milwaukee, and seeing this drastic variations from the water temperature from 20 down to 12 to 14 Celsius, and actually hopping back and forth depending on onshore, offshore winds here. That was captured really well, and that actually is now part of the HRRR model version 4, to be able to capture that. This is an example I just pulled off yesterday, looking at differences in the skin temperatures. Actually, this would have been from last night. So you can see even now also Winnebago is showing up. It looks like probably 10 degrees warmer in the HRRRv4 than HRRRv3. And presumably these values here down into the 30s, that's too cold for Winnebago. Right now you can see also while the Minnesota lake temperatures, Red Lake, so on, are still pretty cold. They are not as cold as in HRRRv3, and that's from this evolution through the lake model. We haven't made change in this, but it's good for you all to know that we actually use the atmospheric data simulation also to modify the soil temperature and the moisture overall, and that actually continues, and that is actually helpful for avoiding big soil moisture errors in the evolution of the RAP and the HRRR model. And similarly, we actually use the NESDIS snow ice analysis, which comes out every day, and having that evolve. And so we actually do snow trimming and building based on the daily snow cover field, and that's been pretty critical in allowing then the evolution of the RAP and the HRRR snow and snow water equivalent to be able to be matching the overall snow cover. Okay, looking a little bit further into the physics, at 3 kilometers, we have found, and maybe it shouldn't be surprising, that even at 3 kilometers, we can't resolve clouds like this here, these smaller clouds. They're maybe at the scale of 1 kilometer. At 3 kilometer resolution, we're able to resolve at best maybe 4 delta X, but probably more like 6 to 8 delta X. So maybe we're able to resolve 20 kilometer scale clouds, but that's not the way the real world works. So there is a representation of subgrid scale clouds that was already in the boundary layer scheme, the MYNN scheme, but that's been adapted to a closer look in that by our colleagues Joe Olson, James Kenyon, and others. It's described actually in an article in BAMS last year. And we actually had a couple of areas where we changed the limit to the the cloud water in the subgrid scale cloud, and then also in the effective radius for the subgrid scale clouds. And that actually resulted in a big improvement in the overall comparison with the downward shortwave radiation. Many of you may know that there's about a 14 station network with radiation run by NOAA with other partners. And so we've been comparing the forecast from the HRRR and the RAP and found this excessive amount of downward solar running, especially in the summer season, 50, 60, 70, 80 watts per meter squared. This is daytime only. And now with this change to the subgrid scale cloud, now we have a much better representation. So the HRRRv4 has this change to the subgrid scale cloud that has big effects in a lot of the subsequent examples we're going to be showing you. In fact, here's one right now, one from last fall, just looking at a forecast over Colorado. Here's Denver in the middle here, and these are 34-hour forecasts in which the HRRRv4 was able to retain this cloud deck. This actually is looking from the 30th and then looking over into the, I guess, the new fiscal year, right? On the first. So this is a day cold front passage, and the clouds in the stratus definitely were able to stick in there, and the HRRRv4 with the new representation of the subgrid scale clouds was able to retain that much better. This is actually an example looking at the actual sounding structure here from the HRRR. So you can see, yes, retaining that saturated layer, whereas the HRRRv3 was unable to do so. We've also been able to see this again from Joe Olson and his work doing comparisons, looking at versus visible images, and we can kind of simulate that in one of the output fields, this output outgoing shortwave radiative flux here. And you can see there's just more of a representation of these small cumulus clouds, certainly over the southeast in this case, but it could have been also over central region offices here. You can see differences in the in this case in the Intermountain region, and certainly in the marine cloud representation and closer to that of reality. That has an impact in lots of areas, but one of those areas is dry line propagation. So in the operational HRRR, we've had seen this happen often, the dry line moving too quickly from this warm bias and having this erosion too quickly of the low-level cloud deck. And so with the new version of the HRRRv4, then it went to a slower speed. Sorry about my jumping around here, but that was closer to what was actually shown, what occurred in the actual surface analysis. So this is a good result here overall. We do have some amount of information that's coming out on new products, but I'm going to go back here. Are there any questions at this point in this quick outline of some of these physics changes and in the model changes?
Yes, Stan, there is one that just came in. On slide 20, not only are the small lake temps improved, but also the overall skin temperature is much lower, or approximately 10 degrees Fahrenheit. Is that the warm PBL bias fix in action?
We do think that's some of that. That's right. It's contributing to that also. So a couple things working together here. Thanks for whoever noticed that point. That is the case.
Okay. At this point, that was the only question that
okay.
came in.
Yeah. Thanks for asking. Yeah, the interaction with Central Region obviously has been pretty critical in doing that, and want to call out the White Lake Detroit office with Greg Mann in particular, working closely with us in that area. But to the benefit, obviously, of everybody in the HRRR domain. So we'll hop ahead. We do have on the HRRR and RAP pages, we've had put together a new tech memo that kind of describes how we look into the HRRRap diagnostic fields. And now, you know what, I'm going to try to pop over to that and see if that works here. I think I will not try to do that. That was a mistake. But if you go to the HRRR and RAP web pages, you can see this. And so it's a new document. Ed Zoke, Eric James, others have helped in putting this together. So it allows a more improved, a little more detail. How do we actually do these different diagnostic variables? So I urge you to take a look at that. Okay, about how we do the cloud cover. There actually is a cloud fraction field, low, middle, high, that comes out. I don't know if you guys looked at that, but we did hear that in the past that was being used. And what was taking place was this use of the explicit hydrometeors from the Thompson scheme and the HRRR model, and then just doing some kind of horizontal smoothing of that. And this would be a typical look at the cloud cover in this cloud fraction field. But what we are doing now is not to use this kind of representation, but out of the MYNN boundary layer scheme, we actually have a diagnostic every time step of the cloud fraction at every grid point here. So this is the subgrid scale cloud fraction that's being used. And out of that, then, we are able to estimate a more precise, we're not saying it's perfectly accurate, but it's more physically realistic in the representation of the cloud cover here, going from, you know, a full 100% cloud coverage, but through this fractional coverage area, which actually is coming out of the boundary layer scheme. So that's a pretty great improvement. This is actually an example of something that's showing up, being described a little bit more in this tech memo that you just saw referred to. This is actually looking at an example here, the HRRRv3. This is actually from last fall, from October, the cloud cover for the lowest layer from the HRRRv4 versus the HRRRv3 versus HRRRv4. And you can see part of that, even though I know this isn't Central Region, but it could have been, over Texas here, this representation of the scattered cumulus. And so this partial cloud representation is doing an excellent job in seeing that in about the right place. This is an example here now also out of the numerics, but in the HRRRv4, we have fewer warm sector oversized cells showing up, and that is maybe a little hard to see, but just fewer of these cells taking place. This actually, even though we're not zoomed in, these kind of cells would be too large, and we would have an excessive number of these in the HRRRv3, and we have fewer of them showing up now in the HRRRv4. And the cells that do show up will tend to be a little bit smaller in scale because of these changes to diffusion and the boundary layer mixing. Regarding snow, there is a snow depth accumulation, and many of you may be aware of that. There's a 10-to-1 snow to water product that's put out by the HRRR and the RAP model, but also there's a variable density snow product, and actually that went out with HRRRv3, having these variations in the density based on the temperature at the lowest level, and that has been modified based on, I guess, I'm sure comments from some of you in the field and people on our team. Trevor Alcott, John Brown were involved in this. Debbie PC was also involved in this. And so now having kind of a minimum 8-to-1 ratio, but then a maximum of as high as 17-to-1 in the snow to liquid ratio. Regarding near surface wind output, there actually are several products. Many of you know that there's a wind gust product. A description of how we do that is actually in this tech memo, a little bit better than what you've seen in the past. But we also have, of course, the 10-meter instantaneous wind itself. There's a product on the maximum 10-meter wind over the previous hour that is output. And then finally, the A-meter wind actually is available also. All of these have been found to be useful in different kinds of situations, and we've been using themselves. Ed Zoka, if you're on the line, do you want to say anything more about this? See if you can even unmute yourself there.
Hold on, let me see if I can unmute. All right, Ed.
Okay, yeah, I was going to say I'm here, but I can't unmute. But I don't know, Stan, I don't have too much more to say. I like to use the, we found in higher wind events, the 10-meter wind gust or the 80-meter wind. Maybe look at both of those, because they're sometimes if the mixing isn't as if there's more mixing, almost it looks like the 80-meter wind sometimes works better. So in cases of some of these bow echoes and things, both of those seem to work well.
Great, Ed, thank you. And Ed, I'm going to invoke you again here in these case studies in a couple minutes, okay?
Okay.
Great. In fact, actually, here we go right now. We actually have 3 cases here now. They're all from last summer. One is this heavy precip case in Kansas City. One is a separate summertime Colorado low stratus situation. And the third is a derecho case from Wisconsin. But are there any new questions that might have arisen about any of these products so far?
Well, no questions at this point, but there was one comment. Someone saying that they would love to see an hourly peak wind gust grid as well.
Okay. Yeah. I guess the way I would say this is that this is kind of a crude way. The wind gust calculation, which you'll see in the tech memo, is just kind of looking at the boundary layer depth, which we think probably doesn't modify too much over an hour. It can in some cases, but it's just looking at the winds through the boundary layer and then making some crude assumptions about how those might be intermittently mixed down to the ground. By the way, I should point out, looking at this slide here, this should be a wind gust potential. Wind gust potential. In other words, we're not saying that's our best forecast at a specific time, but you're saying that, I guess the comment to see a max over the 1 hour would be of interest. Let us look into that and comment back on that later on.
And it looks like Curtis Alexander was wanting to chime in. So Curtis, please. I'll unmute you. All right,
Yeah,
Curtis.
hi. Yeah, can you hear me?
Yes.
Yeah, thanks for asking about that. I know we've had a discussion about this in the past of providing an hourly maximum gust. Part of the challenge is, as Stan has or will, discuss here, there's a diagnostic that's involved in looking through the model column to figure out the momentum excess potential that could be brought down to the 10-meter level. To do that every time step, to compute that for an hour at every single grid point could be a bit computationally expensive. So we have to figure out a strategy to best try to estimate that potential if we were to try to produce an hourly maximum gust estimate. So there's a little bit of technical challenge in how we could most efficiently do that, but it would effectively involve vertical searches at every model column, at every model time step to try to do that. So that's why we haven't previously made that particular diagnostic readily available.
Thanks, Curtis. That's great. We are now about to look at these 3 case studies. We've got 14 slides about that. After that, we'll talk a little bit about the smoke, the HRRR ensemble, and some of the verification, which are pretty good results overall. So that's we're going to head off here. I think it's 10:20, 11:20 Central Time. So I think we're in good shape. Thanks for your questions already. So Ed, would you like to narrate these for a few minutes? Justin, if you could unmute Ed again, allow him to. Great.
Nope. There you go, Ed. I see there you go. I think you're unmuted now.
Yeah, I was just gonna say muted up. Can you hear me okay?
Yes, we can.
Okay, great. So yeah, the main point here is I was actually in KC for a meeting, and there was this potential flash flood event, and this is the result of the rainfall that occurred pretty much after 0Z leading up to the 1st of August. You can see there's a band of pretty heavy rain just to the west of KC. So the main point of this, let me see if I can do this.
Why don't you tell me when you want me to advance, Ed?
Oh, yeah, advance now, sorry. Yeah, you're the guy in control. So yeah, normally we'd have forecasts all along the bottom here, but from our website, we were having a little trouble. But the main point of this one is that I wanted to point out that at 48 hours, which you now have with the HRRRv4, we actually saw this band of heavy rain to the west. And then if you go to the next one, Stan, I'm comparing on the top row the HRRRv3 with HRRRv4, and I think the forecasts aren't that dissimilar. You could argue maybe slightly keeping it more to the west on the new HRRRv4, which is HRRX in this figure, and these are runs leading closer to the event. But the main point, I think, is the consistency. And I'll do forecast shifts occasionally, and I'll find sometimes people forget that the HRRRs run every hour, and it's useful to say, yeah, I looked at the HRRR, but I'm kind of big on the trends. If I see something like this over and over again, I think this is a pretty good indication. Maybe it'll, for instance, in this case, stay to the west. If you go to the next one, Stan, I don't know if we have another one. Yeah. So most of it kept it to the west pretty much through the entire period and kept a pretty narrow band. So pretty good forecast. Stan, if you go to the next one. Now, this is one area that we are really keen to in the Boulder office, but certainly any place along the Front Range or near high terrain, is this business of trying to retain low-level cold air and often with it low clouds. And this can really be a big issue, not just with the HRRR model, but with other models as well, especially in the presence of dry westerly flow aloft, because the models, all of them pretty much with somewhat limited amount of vertical levels, will try to mix that dry air down. And interestingly, when I've looked at some of these, and I've looked at the European model, even though it has lower resolution, sometimes it does have twice as many vertical levels, and we found sometimes it does better. So here's a case comparing the HRRR with the HRRX again. I think from last August, yeah. And you can see geocolor imagery on the upper right showing the low clouds in that first one. And then I'm going to compare just to the analyses thereafter. But what you see is they both start out pretty good, but then as we go through this pretty quick into it, the HRRRv, the version that we now have, pretty much loses everything by 15Z. That wasn't the case. The HRRR new version, much better job of holding on to this. And this is a big improvement. We've seen this in many cases. Not always perfect in the HRRRv4, but it certainly is a heck of a lot better than what we had before. And then this one, yeah, that's good, Stan. This case here is pretty interesting. This was a bow echo type of deal here with, there were two lines. So the first line was a very good success, good comparison with the HRRR2 version. So if you go to the next one, I think this is, yeah, it's a little, this is just the reflectivity, yeah, reflectivity history itself. So this business started out with a complex in Minnesota. Overnight, it becomes this nice bow echo. So it's ongoing. That's the important thing here. At around 9Z, I think that's when our forecast is. You see a nice bow echo, and then it continues to plow its way. It looks like it gets disorganized, but it's actually still producing severe wind gusts all the way through Wisconsin into Illinois. And then there's a second one that does develop behind it. So now if we go to the forecast, these are just, that was just MRMS, composite reflectivity. So here we are at 9Z. So remember, again, the verification, the MRMS is repeated on the right side. We're looking at composite reflectivity, and HRRR version 4 is in the middle, version 3 on the left. So they start out very similar. They have the bow echo structure and everything. Now, one thing we have found, you know, how can you hang on to this structure? And this is sometimes perplexing, and Stan may say a few things about this in a bit, but you know, there's different reasons. Why would you lose it if we don't necessarily analyze the forcing the best? Maybe we don't hang on to it. Otherwise, there's a latent heating applied to give you the updraft. So you go back there just a second, Dan, to stand to that first one. We see that we retain it, and we in both of them we lose some of the structure. But if you go to the next one, by 2 hours in, we really lost a lot of it in the current version of the HRRR on the left, and it's really falling apart by 3 hours, whereas we still have it. It's behind the actual echo, but we still have something there. And if you continue to the next one, we see that does grow upscale in a better bow. It is playing catch up a little, but it's much better than the other forecast. If you go on, the other HRRR, the original version, really loses it totally. This version keeps it going, and we produce this nice, you know, yes, it's a couple hours behind, but it did produce, if you go, well, we don't have that one, but I actually had the wind gust product. It produced a lot of strong winds all the way through Wisconsin into Illinois, whereas the HRRR version 3 never produced any strong winds because it lost the system altogether. That was a real good success story. So I think that's it, Stan, isn't it?
Great. Any questions on those selection of cases that we picked out there?
Let's see. I don't see any questions at this point.
Okay.
And I have lots of other examples. If anybody would ever want to use them in a, you know, a WFO training or whatever, just let me know.
Great. Thanks very much, Ed. On to the smoke business. So this has been kind of under development, but you know, our information from our satellite colleagues in NESDIS, from VEERS and MODIS, having this new product here, the fire radiative power, and being able to pick out these thermal signals, and having a way to be able to identify that and try to eliminate false alarms. But that actually has been used then very effectively in using the degree of the temperature anomaly to estimate what the plume rise might be. So this is just showing some examples here. This is actually from a couple of years ago, but this is actually showing a forecast of the vertically integrated smoke. Yeah, it's true that the fires tend to be over the western United States. They're not always there. There are smaller signals that will show up from brush fires and so on over every part of the country. And this actually is showing the transport, which obviously can affect our downward solar radiation and even our predictions overall, public predictions. And you can see in this case that the smoke absolutely was moving into the Midwest, in fact, across the country. Some of you may remember that. And that actually has made a difference in the temperature bias. So having improvement here in the biases overall. So kind of too high temperatures, but then the HRRR model, this is again the new version with the smoke, is starting to have an effect of that smoke in some of these differences here for this particular case. It makes a difference in the wind biases, lower winds also, if there's less mixing. Okay, so again, this is a slide we had before. The HRRDAS is running, but we do have the experimental HRRR ensemble that eventually, when it comes into operations, we hope for FY23, that'll be part of this FP3 based rapid refresh ensemble. But we do have this right now, and so we continue to run this. We have the data assimilation with the 36 members, but then what happens is that we have these 9 members that we run out every 6 hours. And let's see if I find an example here. This is actually a case for which the HRRR operational missed completely about a case in the southeastern United States. I think this might be 2018. Curtis, if you're online, can you comment about this case?
Yeah, Stan, thanks. Can you hear me?
Yep.
Yeah, so obviously, while we're not making the HRRR ensemble itself part of this HRRRv4 implementation, it does, as a experimental real-time system, provide us with an opportunity to let forecasters see regions of uncertainty, areas of the U.S. on a given day where the forecast errors tend to be higher. The ensemble gives you an ability to look across other solutions that all should be equally likely, and you can see areas where, for example, in this case here, convection that was developing during the daytime on this event in the southeast, that the deterministic forecast simply never depicted, but there was enough uncertainty that the way we sort of perturbed the initial conditions across the different members demonstrated that with not too much change, some of the other solutions painted that exact scenario. So it is an example of the value of adding an ensemble of solutions to a singular deterministic case. And there is, of course, the underpinning of the deterministic system is leveraging ensemble information with the HRRR data assimilation system as part of HRRR version 4. So there is some benefit of that ensemble information going into the deterministic forecast. But again, you get one shot with a deterministic forecast. Having the ensemble solutions gives forecasters an idea of where you may have some greater uncertainty, and you can depict, in an example like this, where you have the potential for a significantly different evolution than what was captured by the deterministic solution, given the degree of uncertainty that exists there. So having that net of solutions certainly has value.
Curtis, maybe you can comment on this case also.
Sure. So this was another event that took place about 2 years ago, and we were looking at real-time experimental HRRR ensemble forecasts. And this was a case where this was earlier in the day, so it was a major sort of training convective event over Oklahoma. So heavy precipitation occurred from a southeastward building convective complex across southern Kansas into Oklahoma, and it did result in some significant flooding impacts in Oklahoma City area. And the ensemble system at the longer forecast lengths had 1 or 2 members that were depicting this scenario out of about the 9 produced. And those are shown here, highlighted at arrows. So there was a little bit of signal at about the 27 to 30 hour forecast length that a scenario like this southward building MCS could occur into central Oklahoma. And I think with the next slide, okay. So the point was at shorter forecast lengths, the more and more of the ensemble members picked up on that scenario. And so there was increasing confidence as the time drew nearer that a scenario like that was going to unfold. And some of that information can be conveyed in other ways, whether you look at the ensemble maximum or the percentiles of exceeding a particular rainfall rate, for example, from the scenario over a particular region like central Oklahoma, where you can convey that ever increasing confidence or certainty that more and more of the members are painting that type of solution. So this is just another example how to leverage some of that ensemble information.
Yeah, we appreciated seeing in the Science Center last week, Science Circle, about the use of looking at the Warn-On forecast. And so obviously this is closely related to that. Another example, Curtis, if you want to comment on this one.
Sure. So this is an evaluation that was conducted during the spring forecast experiment at the Hazardous Weather Testbed in Norman last May, and sort of showing a comparison of different ensemble systems for trying to highlight severe weather potential in the Southern Plains. This was obviously one of the more scrutinized days. This was May 20th. I think this was a high risk forecast event across Oklahoma. There was obviously a significant amount of severe weather reported. I think in the end, the amount of warm sector activity was less than what may have been anticipated or forecasted by the model guidance. But that said, it sort of demonstrates different approaches to constructing a storm scale or CAM ensemble system, whether it be the HRRR ensemble at the panel at upper middle versus the HRRRv, which is current operational CAM ensemble system, or some of the other research ensemble systems being contributed. We found that the HRRR ensemble system, it had a lot of development on it in the last couple of years and has been gradually making progress in terms of getting adequate spread skill. And so I think, we're getting closer and closer to that point where we're going to be able to, I think, achieve a single model ensemble system to help match the multi-model ensemble system that HRRRv currently provides. It'll make us, easier down the road to maintain a single model system for an ensemble design rather than multiple different dynamic cores trying to sustain that development. So that's kind of a research area where we're heading and trying to move the HRRR ensemble system forward. And again, that's going to, a single ensemble system design is going to be, or single model for a CAM ensemble system is something we want to put forth for the rapid refresh forecast system, which is going to be the DCAM system for Unified Forecast System era, or UFS.
Okay, that's the last slide we had in the HRRR ensemble. Any questions show up, Justin, in that area from anybody?
Yes, we just got a few. So one question, curious if you know the date of the ensemble system depicting a QLCS across Mississippi, Alabama, whereas the operational HRRR did not have any convection.
Oh, this case, are you talking about here on this slide?
I think it is this one.
I believe that's the case.
I'm gonna have to look at that up. This was certainly more than a year ago. I don't have that off the top of my head, but I can certainly dig out what that date was.
Yeah.
For that.
I tried to look that up too, Curtis. In fact, I think you and I had an email exchange in this a few weeks ago.
Yeah, I can. It'd probably take me 5 minutes to find it. So.
Okay, we'll tell you. We'll spring along here, and you can dive back in here.
Yep.
Anything else, Justin?
Yes, there was another question. So, will the HRRR experimental use of version 4, or will it remain using version 3?
Curtis, you want to take that one? It is version 4, absolutely. So
the experimental HRRR that's being provided from GSL is version 4. And that's what's now running at NCO in a parallel version, and then hopefully will be implemented operationally later this month. So at that point, you'll have an operational HRRR version 4 produced from NCEP, and our experimental version will still be HRRR version 4. What happens to our version after this is still up for some discussion and scientific planning to figure out how we want to leverage that going forward. But both are version 4 reflective at, right now, the NCO parallel and the one produced from GSL.
Okay, and that was the last question that we have received at this point.
Okay. We just wanted to give you a quick heads up. We've been looking at verification of these versions of the HRRR and the RAP, by the way, kind of consistent in many aspects, but this is actually winter time retrospective comparison that we did here from February 2019. And so showing that for 6, 12, 18-hour forecasts, the RMS errors, this is over the eastern US, is lower overall. So this is due to a combination of things, better boundary layer scheme, also improvements even in the way we diagnose with the snow model in the land surface model, both those contributing. The bias here is, you can see that it's a little bit in the cool side, and I think we've seen that also in this last winter. Not drastically so, but it's had a cool bias in the winter of a few tenths of a degree overall. So good for you forecasters to be aware of that. This is now a result from a retrospective run in this spring, the month of May 2019. So you can see here that the RMS error for the 2 meter temperature is again about the same or maybe slightly better here as we go into the daytime hours. By the way, this is kind of by time of day here. The bias, this is now where you can see in the current operational version, the warm bias definitely was showing up here. And so now we're looking at close to zero bias, but maybe a little bit of a cool bias around 0Z. That's the one thing we've seen overall. So sometimes we did notice initiation of convection slightly delayed with this. Maybe it was too fast before with the warm bias. This is now looking at dew point prediction. So this is again going back to the February cold season. So having a better RMS error here for dew point to whatever extent it's worth. This is again over the whole eastern US. And then the bias is slightly better. Been running a little high in the winter time, and that bias in the daytime especially is a little bit better. Now looking at dew point in the May season. And so the RMS error for the dew point is slightly better overall in 6, 12, 18-hour forecasts. For a short range forecast, we didn't see a whole lot of change in this moist bias, which actually was evident. As we went out to 12 and 18-hour forecasts, you can see that this moist bias was reduced. The vertical axes don't match here exactly, but this is definitely an improvement in the 12, 18-hour forecast in the moist bias. We looked also at ceiling forecasts, pretty uniform improvement here overall for LIFR, IFR, and MVFR ceilings, having a total skill score better here, and also the frequency bias. One is the best here, so we've run now to a slight high bias in these events, but not drastically high overall, and we definitely had a low bias here for the 3,000 foot ceilings, and so we think overall this is a good result and consistent with that improved low stratus retention. This I think is looking at in a fall case here. This is actually looking at visibility now. So improved less than 1 mile, less than 3 mile, less than 5 mile visibility. In all of these situations by forecast hour, seeing an improvement overall. And especially for the 3 hour and 5 hour, we had not so frequent having these low vis cases showing up here, and now we have an improved bias. It's not all the way up to 1, but it's closer to that. We put in a couple of graphics. Justin, I assume we'll just dump this PowerPoint on you. You guys can have that, but Curtis put some really nice graphics together here for those who can actually punch on it directly, but having where to get an information about the actual grids from the pre-operational RAPv5, HRRRv4. They're available in Nomads already, so these are new entries right here. Actually, the RTMA experimental is available as well as the HRRE data sets. And then there are graphics that are available for the experimental versions. EMC has a comparison website that Alicia Bentley put together, really nice. But now we also have the MAG website has comparisons that are available. And then, of course, the GSL, GSD website have these data sets. So this actually is kind of the last slide here. So I'll ask another opportunity for questions here in a minute, but here's what we expect 3 weeks from yesterday to have this new version. So the HRRR and the RAP coming through here. The physics improvements, the smoke prediction are going to be noticeable. Actually, I hope we don't have an excessive smoke season this summer, but we'll see what happens there. But we're prepared for that now. And we have overall, we think, an improved cloud storm precip prediction. The ensemble data simulation really helps definitely in the first several hours, the extension to 48 hours. And so this improved cloud storm prediction is probably a key aspect. The 9-member HRRRe will continue this year experimentally. In 2023, just looking ahead here, we'll have this moving toward the FV3 based RRFS. We can tell you more about that later, but at that point, we do anticipate having the full ensemble prediction. So again, a couple of link here to the new tech memo. You can get that off the HRRRap web pages to understand more about how these variables are diagnosed. And actually, we do have a QA email address that we welcome you to send emails. This will go to several of us, and then we can respond. We are so grateful for the regions and the offices to do many of that over, I guess, the history of our time working with you all with these hourly updated models, and that's been terrific. So that ends our presentation, and welcome any other questions that haven't already shown up.